We're going to work with the heat curve today. We made one last time. Okay, you should have had a basic heat curve that went sort of like this. Okay, with temperature on the x-axis and along the y-axis time. And you had a lot of 100s, right? It took forever at the 100. Not so much as the 0, but a lot of you are asking, can I stop? Can I stop? But then you got that little blip at the end. We're going to do some problems now with the heat diagram. Who remembers at the slope area here what equation we put in on our heat curve? Q equals mCp delta T, right? On the slopes. When we had the flat area, we either used heat of fusion times molar mass, mole or mass, or heat of vaporization times molar mass. We need those numbers, so let me put those numbers up. You might want to either put them on your heat curve because you're going to be using it a lot, or in your notes, doesn't matter which one. So we need delta H of fusion for water, and we're going to just be using water, is 40.7 kilojoules per mole. Oops, sorry, that's not fusion, that's vaporization. I looked at the wrong one. So heat of fusion is 6.01 kilojoules per mole. And then we'll also need some CPs. The CPs are different for each of these different levels right here. So the CP for ice is 2.03 joules times degrees Celsius per gram. The CP for water is 4.184 joules times degrees Celsius per gram. And the CP for steam, or vapor, or gas, depending on what you call it, 2.01 degrees Celsius times joules divided by grams. So those are the things that we will need to be able to do problems with the heat curve. So first up, I'm going to start with a simple problem, because we want to do simple before we go more complex. We're going to start with a cube of ice, and it's 10.0 grams. Okay, so I've got ice, and I'm just going to melt it. I'm going to start with the ice at a negative 10.0 degrees Celsius. Okay, so I am going to be going through Q1 and Q2. Those are the only parts I'm going to go through. And I'm going to start here at Q1 at negative 10. And I'm just going to go right to where the point where I would start heating my liquid when I've melted all my solid. So the first Q is on a slope. So that Q1, I use mCp for ice delta T. Everybody okay with that? So I'm going to plug in the numbers. So mass 10.0 grams times by specific heat for ice 2.03 joules times degrees Celsius per gram times by the change in heat. I'm going from negative 10 up to 0. So what's my change in temperature? 10. So 10 degrees Celsius. At this point, degrees Celsius and grams cancel out. 10 is going from negative 10 here up to 0. Okay? All right, so if somebody plug that through a calculator, let's get an answer here for Q1. One more time. 203 joules. Now, you'll notice that heat of vaporization, heat of fusion are given in what? Kilojoules. So we want to change those joules into kilojoules. How do I do that? Basically divide it by 1,000. In 1 kilojoule, there's 1,000 joules. So I'm going to get over here 0.203 kilojoules. Okay? I'm going to need that later, so I'm going to underline it. It's not the final answer, but I'm going to need it. Okay, Q2, I now have all my ice at 0 degrees. Now I want to melt all that ice so it's liquid. Okay? So now I'm going to take and I'm going to use the heat of fusion, and I'm going to times it by moles because the heat of fusion is given in kilojoules per mole. So I'm going to take 6.01 kilojoules per mole, and I'm going to times it by 10 grams of water, but I got to change that 10 grams of water into moles of water. So if I add up 2 hydrogens and 1 oxygen from the periodic table, I get 18.015 grams of water is equal to 1 mole of water. Sorry, I'm squishing it in here trying to make it not go over. So going through to cancel. Grams of water cancel, moles of water cancel. I'll be left with kilojoules. So for Q2, what did we get? So 6 times 10 divided by the 18.015. What do we get? 3.34 kilojoules. Okay, now to get the total amount of heat I need, all I have to do is go Q1 plus Q2. So I'm going to take 0.203 kilojoules and add to it 3.34 kilojoules, and I get what? 3.543 kilojoules. That's how much energy it took. I only went through 2 phase changes, or 2 things. I only heated up my ice and melted my ice. That was it. Okay. 5. So you got to heat the ice, you got to melt the ice, you got to heat the liquid, you got to turn the liquid into steam, and then heat the steam. That would be the max. Okay. So let's do another one. This time we'll do 3 instead of 2. Okay. Then we'll do a maximum one that has 5. Okay. So going on to the next one, I'm going to make it easier for you because I'm going to choose to have ice that is 18.015 grams, which is equal to 1 mole of ice. Okay? Because that's what 2 hydrogens and 1 oxygen add up to. I'm going to start here at a negative 30, and I want to take it to liquid at a positive 45. And these are degrees Celsius. So on my chart over here, I'm starting right here at negative 30, and I'm going to here at a positive 45. So looking at it here, I'm going to have Q1, Q2, and I'm going to have Q3. Okay? I have to break it up because every time I hit another thing, I'm going to go from negative 30 to 0, then a 0 to 0 where I change from solid to liquid, and 0 up to 45. So I'm going to have 3 Qs. Let's look at the first Q, Q1. What equation do I use? MCP ice delta T, good. So I'm just going to plug in. So mass is 18.015 grams. CP of ice was 2.03 degrees Celsius times joules divided by grams, times by delta T. What's my delta T for this first one? Well, I started at negative 30 and I'm going up to 0, so it's going to be what? 30. Degrees Celsius times joules divided by grams. Okay? Things that cancel. Grams, degrees Celsius, times it through for me. What do we get? Oh, what's the other thing we need to do for this because it's in joules? Divide it by 1,000 to get it in kilojoules. So we end up over here with kilojoules. So once you get your answer, divide it by 1,000 so we can get it into kilojoules. So we ran out of room. We don't want to take too much. What do we get? We got it done? 1.097. Anybody else get that? Awesome. Okay, then I'm going to change colors for this next Q so we can start to keep track of it. So Q2, what's happening at Q2? Staying the same temperature, what's happening? I've heated my ice up to 0. Now what am I doing to my ice? Melting the ice. So when it's flat, then I'm doing a phase change. The first flat area is melting. Second flat area is changing it to steam or boiling. Okay, so this one I'm going to go heat of fusion times by mole. Since we've already converted up here, we know it's 1 mole. We'll make it real easy. Heat of fusion, 6.01 kilojoules per mole times by 1 mole. Gives me 6.01 kilojoules. See how I made it easy for you? Okay, then we're going to go to Q3. What's happening at Q3? I'm increasing the temperature of the water. Now it's all melted, now I'm increasing the temperature. So because of that, I'm going to use mCp water times delta T. So my mass, 18.015 grams times by, what's the CP of water? Good, 4.184 joules times degrees Celsius divided by grams. And what's my change in temperature for this one? 45. Okay, so canceling out degrees Celsius, canceling out grams. I think I've got that wrong. I think degrees Celsius is on the bottom, guys. In fact, I know it is. So I've written that wrong. It should be degrees Celsius on the bottom. So in your initial one, whatever it was back here, let's go back here. This should be on the bottom. So fix that. Grams is still on the bottom. Grams is still on the bottom. Sorry, that was my mistake. So quickly fix that. So my equation, my stuff won't. No, no. I just put it in the wrong place. Degrees Celsius should have been on the bottom. So it'll cancel out. Okay. Yes, please divide it by 1,000 because we want them all in the same units. Okay, so we're back here. Same units. 3.39. Now I like to do it this way where all of them end up on the same thing because then all I have to do is add them up and I've got my final answer. So what do we get for final answer? Is that what you got? I gotta practice my adding skills every once in a while. Is that what you got? Is it 10? Did I see I screwed up? So, got to practice them more often. 498? Yeah, 497. Okay, so this is another one. Now we're going to do the biggest one we could with all 5. Okay, so we're going to do another one here with all 5. So here I'm taking my block of ice. I'm still going to give you that 18.015 grams so that we know it's 1 mole. Okay, sometimes it's easier to do that conversion right up front. Whatever you've got, change it into moles right up front because you're going to be using it if you go through all 5 twice. So it's easier to convert it once. Say we start here with a negative 45 degrees Celsius this time, and I want to go all the way up to steam. This is my steam pitcher at a positive 135 degrees Celsius. Okay? So it's just step by step. Okay, so I'm starting here, negative 45, and I'm ending up here at 145 degrees Celsius. So on this one, I'm going to have Q1 up to 0, Q2 changing phase, Q3 going from 0 to 100, Q4 changing phase, and Q5 changing temperature of the steam. Okay? So, yes. Oh, I put 145. Sorry, 135. Thank you for fixing that for me. Okay, so starting Q1. What is Q1's equation again? MCP ice delta T. So plugging in 18.015 grams times by 2.03 joules divided by degrees Celsius grams times by, what's the change in temperature? 45. Okay. Divide by 1,000, yes, because it's in joules. Okay, so we can get kilojoules. Everything should cancel but the kilojoules. So what do we get for our first one? 1.65. Okay, let's go on the second one, Q2. What's the equation for Q2? Heat of fusion times moles, right? This one was the easy one. So heat of fusion, 6.01 kilojoules per mole times by 1 mole. Moles go out. 6.01 kilojoules. Okay. Q3, what's happening? MCP water, good, times by delta T. So mass again, 18.015 times 4. That's grams. 184, thank you. Grams degrees Celsius times by, what's my change in temperature? 100. 100, good. And we're going to divide this by 1,000 again to get it into kilojoules. Everything should cancel.
Where'd you get 4.3?
That's the CP of water, of liquid.
Where's the 100?
100 is from going right here to right here. Okay? So what do we get for kilojoules for this one? 7.54. Okay, next one, Q4. What's happening here? It's boiling, so H of vaporization, good, times by mole. So what's HVAP? 40.7 kilojoules per mole times by 1 mole gives me 40.7 kilojoules. And the last one, Q5, what equation do I use here? MCP steam or vapor yields delta and times delta T. Plugging in what we have, 18.015 grams. What was the CP for steam? 2.01 joules per gram degree Celsius times by, what's my change in temperature? 35, good. And don't forget to divide that one by 1,000 kilojoules, or sorry, joules per kilojoule. Then everything cancels. .27 kilojoules. Then we just need to add everything up. That is the hardest problem. Okay? That is the hardest one. How do you feel? Think you could do it? Okay. So as long as you don't mess up and put anything else on your heat curve than what I've asked you to put on it, I will probably allow you to use that on the test. Okay? All right. Now, we're going to do a lab next time. So what I'm going to do is I'm going to go over the lab. We're going to be using the MCP delta T in the lab. So I want to sort of familiarize you with what's going on. What we're going to be doing, and you might want to take notes because you don't have your paper with you yet, and so it might make more sense if you write your own little notes to it. We're going to take a piece of metal, and I'm just going to write metal on it. And we're going to get the mass. First thing we're going to do is get the mass. Then the second thing we're going to do is we're going to put that metal into boiling water. And this is my little boiling. And so we're going to be using these little hot plates. Okay, this is my little hot plate thing. So we're going to boil these metals once we've weighed them. Then in another cup, a styrofoam cup, because we can't really afford calorimeters because they're really expensive. So we're going to use a styrofoam cup. We're going to pour in 100 milliliters of water. Now we might have to adjust that. That might end up being 200. It just depends on how much we need to cover the metal. Okay, so we need to sort of look at that beforehand. If 100 doesn't come up to here somewhere, we probably need to add more. Okay, so we're going to add 100 milliliters of water. Remember, that is equal to 100 grams of water. Okay, because it's a 1-to-1 ratio. Then, once we get this to boiling, we're going to take the temperature. And we're going to call it the temperature of the metal initially. Okay, is it going to be 100 degrees Celsius? No. That's only if we were at sea level. It would be 100 degrees. So is it going to be higher or lower? Lower. That's why if you're a backpacker and you go and you take macaroni and cheese with you up into the mountains, it ends up being nasty because it doesn't get high enough to cook it. It sort of just makes it mushy. Okay, so that's something to know. Okay, now what you're going to do is you're going to take tongs and you're going to transfer that metal into here. Okay, so I didn't really, let's see, I didn't keep track of the numbers. You're going to have the initial temperature over here of the water before you put that in, and you're going to have the temperature final of the water. And that's going to be equal to the temperature final of the metal. Okay? So when they all come to equilibrium. Now we're going to have those fancy little probewares. So we're going to be able to get the temperature really fast and easy, which is nice, instead of having to use the old-fashioned thermometers and try and read them. Okay, so it should be really quick. We're going to do several metals. So what we're going to do is, by the law of heat of conservation, whatever heat is gained has to come from somewhere. So whatever heat the metal gave up, the water had to gain. So we're going to set the mass of the metal equal to the CP of the metal, and the change of temperature of the metal equal to the mass of the water, we ran out of room, CP of the water, which we know, times the delta T of the water. What we're going to be looking for is the CP of the metal. And we're going to see experimentally how close we can come to what it actually should be. And we're going to do a percent error. So we're going to practice this in lab next time. Okay, so it's really fast and easy, basically moving, moving, moving. Okay, once this comes to equilibrium, I don't have to dump it out. I just start at a new temperature, and I take my another metal over here, and it started at this temperature, and I move it over here and see how high it goes from there. So I don't have to dump it out and redo. Yes? They're about this big. Okay. Some are small, some are only this big. Okay, but like we're doing zinc and brass and iron and different kinds. No, you know, beaker this big will hold 4 or 5. Okay? All right, so that's what we'll do next time. So this time, the rest of the time is yours to work on the model lab and to work on the worksheet from last time that looked like this, the phase diagram thing. This one, if we don't correct at the end of the period, will be due at the beginning of class next time. Okay? And then the lab, the model lab, needs to be turned in next time. The one that we made the models with, the model lab. Yep, we played with this. That was the one that looked like, I'm borrowing Sam's, looked like this. Okay? Model lab is due next time. Yep. And the worksheet is due next time. Now, did we correct the phase diagram worksheet last time? Awesome, yes. So I think I've got it printed out in here because we did it online to correct. If not, then just put it in and I'll correct it. Okay, so time is yours.